This is the fourth time that I've tried to make this video. I've had everything go wrong, from software getting buggy to I shot this entire video last night and the files are corrupted. So they're lost. There's like 10% of them work. So I'm reshooting it now. Apparently God does not want me to teach you how to make ETN. But we're gonna do it anyway. This time it's gonna work. I promise.
Energetic America.
Explosives aren't hard to make, guys.
Accelerate.
Okay, this is ETN part 2. If you haven't seen part 1, you should probably check it out. We go over some of the sensitivity of ETN when it's in the melt phase. If you can't be bothered to watch that, the cliff notes are that it gets super sensitive. So it's a recurring theme. When you approach the melting point of ETN at 61C, you're going to get heightened sensitivity, practically unsafe to handle. People do it. You can get away with handling it, but it's extremely sensitive. So it's an operation that warrants a lot of extreme care and precaution to prevent accidental detonation. So let's talk about synthesis. You have two broad methods for synthesizing ETN. The classic way, the professional way, industrial way would be to use a mixed acid solution. This is really common for nitrate esters. The other method that is very popular with ETN would be nitrate salt methods. So a nitrate salt method, they're using sulfuric acid mixed with a nitrate salt, and they're making nitric acid in situ. So we'll kind of explain both of those methods. So the mixed acid method, if you go to the original DuPont patent, where they have an industrial procedure they use to produce ETN. It's from the 1920s. DuPont is dissolving erythritol in 90% sulfuric acid below 50C. You can get an effect called carbonization of sugars in general, but erythritol in particular, you can carbonize it if the temperatures get too high, and that changes what you're working with. So you're not going to get the desired product, the ETN, if you have carbonization of the sugar. The ratio that they're using is 1 part of erythritol to 5.5 parts of sulfuric acid. These are parts by weight. And then they're adding to that 7 parts of nitric acid. The nitric acid is described as strong, and during their nitration, they are going into some pretty high temperatures. So they recommend a nitration temperature between 40 and 60 C. Therein lies an issue, and it's very likely that they didn't really produce ETN on any large scale, because they definitely would have had some detonations. 60 C, it's 1 degree centigrade below the melting point of ETN. When you get the change in the sensitivity profile, most likely they were just unaware, because going to 60 C is, it's suicidal. You shouldn't do that in the operation. At no time in any of the operations involving ETN should you approach the melting point threshold without at least expecting heightened sensitivity. So if you're not taking precautions to prevent injury or property destruction from accidental detonation, then you don't want to go anywhere near that temperature. Moving on with the DuPont patent method, they give an alternative mixed acid solution. They quote as a 12% sulfuric and 80% HNO3. Point is that they're using a mixed acid with a lower amount of sulfuric acid, and that is pretty common for nitrate esters. They are then recrystallizing from alcohol, that'd be ethanol alcohol, and they're neutralizing with ammonium carbonate. So this paper's in the 1920s. Ammonium carbonate was used in baking goods a lot back then. It's way less common now. It's been supplanted by baking soda, sodium bicarbonate. But back then this would be typical. I think they call it baker's ammonia is what they used to refer to ammonium carbonate. So that's what they're using. The DuPont patent method is just the first example that you'll see. It's commonly found in literature for preparation method of ETN. I wouldn't follow it. We're just referencing it for historical record. There are some other modern papers where ETN has been produced, and they're using mixed acid methods pretty much across the board. So a few of these, I'll just reference them. We're not going to go into detail, but Bergheim got an 83% yield with the mixed acid method. Oxley got a 75%. Matjes has a paper where he's also getting 83%. So 83% is very common. I've found mixed acid production, these are actually kind of low. You should be getting like 85% plus, depending on exactly the temperature control and the rate of addition and the stirring profile that you use. But 85% is really common. Those are examples of mixed acid nitrations of erythritol. What is much more common, what you'll find, if you look up ETN production on the internet, you're going to get the phone book in terms of nitrate salt procedures that people are trying. People really get wrapped around the axle with the nitrate salt methods. People perceive it as easier than using nitric acid. So a lot of people prefer to go this easy route, mild nitration route with a nitrate salt and sulfuric acid drain cleaner. They geek out online with all kinds of different experimental ratios, and they're really all over the place, and they're kind of, they're not well documented really. So I don't reference those. What I would reference is an ATK publication. They have a PowerPoint floating around online. They had an experimental trial of using nitrate salts to produce nitrate esters. Most of them they're producing are, liquid explosives that they're using for rocket motors, but they also make things like PETN, which would be the most analogous to ETN. So I would reference this ATK PowerPoint as a good explanation for what is going on and a good target of how to do a proper nitrate salt sulfuric acid nitration. As an explanation of what's going on in a mild nitration mixture of a nitrate salt sulfuric acid, you're taking a nitrate salt, typically ammonium nitrate, sodium nitrate, potassium nitrate. You are mixing it with sulfuric acid, and then out of that you're going to get a multi-phase reaction that's continuous. The first part of it, the target reaction, what you want is the production of nitric acid in situ. That means that it's made inside of the reaction concoction with a lot of other products. But you're getting nitric acid in there, and then you're getting whatever cation, ammonium, sodium, or potassium, you're getting that as a bisulfate, as another product. These react further with more sulfuric acid, and you get a second round of reactions where you're going to get NO2, H2O, HSO4. So that's hydrogen sulfate and water, and those are, they're not desirable in the reaction, but that's just the cost of doing business when you nitrate this way. That's what always happens. The benefit of using a mild nitration mixture with a nitrate salt is that you're getting really mild reaction conditions. So to give you an example of that, what I'm talking about, if we reference from ATK, we reference the PETN procedure, they are taking 1 mole of penerythritol and they're hitting it with 8 moles of ammonium nitrate with sulfuric acid, an equivalent molarity to the nitrate. They're running this reaction at 2 hours at ambient temperature. So there's not even any temperature control being used in this method. That's how mild it is. And then out of that 2 hours at ambient temperature reaction time, they're getting a 62% yield of penerythritol tetranitrate. 62% yield for PETN is low. You get a lot higher yield with a mixed acid method or straight nitric acid method, but you can get a yield. And when you're doing a nitrate salt method, it is a lot easier if you have issues with procuring nitric acid for some reason, then this is a valid alternative, and it's fairly safe and mild in terms of reaction conditions. So this can absolutely work for ETN. So nitrate salt nitration method with ETN is very similar to PETN. The main differences that I've used in the past, I do some temperature control. So I try to keep ETN, the entire reaction, I try to keep it below, maybe 30 C at the max. If you get too high in temperature, you're going to run into a risk of runaway, even with a nitrate salt method. If you start to get spikes in temperature, that's always a good sign that you're going to go into a runaway. If you see red nitrogen dioxide gas coming off of the reaction, you're definitely going to go into a runaway. The correct procedure for quenching a runaway, for stopping it, neutralizing it, is to dump the entire reaction into a large quantity of water, a dump bucket. That's the best procedure to stop a runaway reaction. I have done a ton of experimentation with nitrate salts. I've used exotic nitrate salts with, I'm talking particularly ETN. So double nitrates, the works. I've tried it all. The exotic nitrate salts aren't really useful. The common nitrate salts, ammonium, sodium, and potassium. And the order of practicality, in my opinion, is, ammonium nitrate will give you a very stirrable, in terms of viscosity of the mixture, stirring it, mixing it. It's very stirrable. It's the thinnest of the mix. Sodium nitrate, on the other hand, will be the smallest mass per nitrates that you're putting in there. So you can have an equivalent number of nitrates, and the amount of material and volume is going to be smaller that you add to the reaction solution. But the products with sodium or potassium nitrate are going to be a lot thicker. You're going to get a thicker mixture that's more difficult to stir. They can get really difficult depending on the nitrate salt that you use, especially with some of the double nitrates. And then there's potassium nitrate. It's even worse than sodium nitrate, in my opinion, in terms of an easily stirred mixture. So potassium nitrate is generally used because it's available as a stump remover over the counter. So some people, that's the only access to nitrates that they have. In that case, it's fine. You're just gonna be doing some extra work. The way that I do a nitrate salt method, I've done it both ways, where I've dissolved erythritol into sulfuric acid and then added the nitrate salt component. I've also made the nitrate salt reaction mixture first, allowed it to stabilize to a good temperature, because you will get elevation in temperature. So I allow it to stabilize, and then I add the erythritol to that. And that's probably preferable, in my experience, to dissolving erythritol in sulfuric acid. In general, erythritol should be added slowly, and you should be monitoring temperature. You really don't want to exceed maximum 30 C. At the end of the addition of erythritol, I just monitor temperature and make sure that it's stable and that I don't get any huge spikes. If you get a huge spike, dump it off. Reaction times should, at minimal be 2 hours, like the patent procedure from ATK. I would say 2 hours is a minimum. I've gone a lot longer. It doesn't really make a terrible difference. You just don't want to go too short. If you go too short of a time, you're definitely not going to get complete utilization of your nitrate salt to create these nitrate ester groups on the ETN. In terms of the quantity of nitrate ions to be adding to your substrate that you're going to be nitrating, erythritol, there's 4 hydroxyl groups in erythritol, so I use ×2 of the nitrate. So if I have 1 mole of erythritol, I'm using 8 moles of a nitrate. That's the general rule. You can go less. People often go less. In my opinion, it's not worth the risk of undernitration. You're just going to get a lot more reactivity and concentration if you
pump those numbers up. Those are rookie numbers.
In terms of sulfuric acid quantity, when you're doing a nitrate salt acid mixture, it's really not so much a matter of the number of moles of sulfuric acid. And minimally, you would want to match. If you did 8 nitrates, you'd want to have 8 moles of your sulfuric acid, because that's necessary for the reaction to take place. But you're going to be more than that, because you're not going to be able to get a stirrable mixture unless you're using excess sulfuric acid. So the amount of sulfuric acid that I would add is, basically eyeballed. I'm just going to add as much sulfuric acid as is necessary to make this nitrating mixture stirrable with the erythritol. Sometimes you even have to add additional sulfuric acid to your nitrating mixture as you're going along, because it becomes too thick. If you have to do that, that's okay, but keep in mind, when you add sulfuric acid, you're going to get a corresponding rise in the temperature, and you just need to be monitoring it and keeping it under at most 30 C. I am not going to spoon feed ratios for nitrate salt method. There's a couple of reasons for that. The first one being that there's so many nitrate salts. I mean, there's 3 common ones, so I'd have to at least do 3 sets of ratios, and I just don't want to do that. But if you're producing ETN, you should understand the molar concept. And this is kind of the second part of it, is that we're kind of creating a riffraff filter here. If you're not willing to understand or learn about the concept of the mole, then you really don't have business producing ETN. I mean, you're not going to be able to produce it safely. So in general, however many moles of erythritol you're using, you want to use 8 moles of nitric acid and 8 moles of sulfuric acid. The sulfuric acid will be in excess, and you want to keep the temperature of the reaction generally somewhere under 30 C. For reaction times, you want to have a minimum of 2 hours, but you can really extend that. I mean, you can safely nitrate for 8 hours if you wanted to, if the situation dictated. The preferred method of production of ETN is with mixed acid. You're going to get much higher yields. Like I said, you're going to get 85%. It should be the low end. There are some people in comments that mentioned they're getting above 90% in yield. So it's definitely the way to go if you're concerned about yield or efficiency. Mixed acid method is just a much smoother reaction. It's going to give you a very clean product. It's easy to process. I highly recommend it over a nitrate salt method if it's at all possible for you. Mixed acid method is simple enough to where I can spoon feed you if you're using a mixed acid. So I recommend, when I'm doing it, I use industrial grade, 68% nitric acid. The general ratio is for each gram of erythritol, I'm doing 3.13 grams of sulfuric acid and 2.58 grams of nitric acid. Now, both of those acids, I'm quoting those at 100%. So you're probably not going to be working with that. If you're working with industrial nitric acid, it's going to be 68%. So the way that you would adjust that is to take the 2.58 grams of 100% HNO3 and you're going to divide it by 0.68 because it's 68%. That's going to give you your corrected mass of nitric acid to weigh out. Same thing with the sulfuric acid. You're probably not going to be using 100% sulfuric acid, so 3.13 grams divided by point whatever the percentage, the known percentage that you get off your MSDS for your drain cleaner. It's going to give you a corrected mass for sulfuric acid. That's the method that I use for mixed acid ratios. And what we're doing here is that's an equivalent of 1 mole of erythritol, 4 moles of sulfuric acid, and 5 moles of nitric acid. In the mixed acid method, it is beneficial to use heavy temperature control. So I prepare the mixed acid nitration mixture, and then I'm going to reduce temperature with ice all the way down to 0°C. And then I'm adding erythritol slowly to the nitration mixture, monitoring temperature so it doesn't get above 5°C. The entire process of nitration, I don't exceed 5°C. The reaction time should be 30 minutes. You can get away with 15 minutes, but 30 minutes seems a little bit more realistic. And you can extend a little bit beyond that if you wanted to. Of course, it goes without saying that, when you're doing a nitration, you're going to be producing a ton of nitric oxide, clear gas that's going to be coming off the reaction mixture. And this is, it's toxic. So you can't breathe it. You have to be venting this. So, the typical way, it's very common, is just to use a box fan in a window. That's good enough. If you're making a large quantity, you might want to consider doing it outdoors to avoid fumes. You definitely don't want to be breathing in nitric oxide fumes at all. After a half-hour reaction time, it is now time to quench the reaction using ice water. I use ice water in the volume of 4 times whatever the volume of nitration mixture that I'm using at a minimum. You can use more water and it's not going to hurt anything, and your ETN product is insoluble in water, so it's going to crash out. ETN isn't ionically sensitive, and so you're not going to have issues with crashing out into tap water. You can use distilled water if you want. When pouring off ETN mixture into the crash solution, you want to be stirring, and this prevents localized heating that occurs when the acid enters the water. Your crash bath that you're using is very acidic. It has all the acidic products from your reaction mixture in it, along with the insoluble ETN, and you now have to filter it. You pour it out into a filter, all the acidic water is going to pour through mostly, and then you're going to be left with precipitated ETN. ETN is notably acidic, in terms of at the end of the reaction, it's always got a ton of acid on it and trapped within the crystals. So you have to do some extra love and care in terms of processing this to make it stable enough to use. So the bare minimum, you have to do a water wash. So you take your filtered ETN and you put it into a container of water. You want to use quite a bit of water because the goal here is to remove surface acid from the ETN. So you want to have a large water bath, put ETN into it, and then you stir it for quite a while. Now that the ETN has been through a water wash, you can filter it again, and the remaining ETN now needs to be checked with a bicarbonate solution. So you should make a 5% sodium bicarbonate solution in a jug and then pour it. I like to pour it over the ETN. If you did a good job with your water wash, you're not going to have a lot of reactivity. You're not going to see a bunch of fizzing. Most of the acid is going to be removed. It's going to be only trace acids that are going to react with the sodium bicarbonate in the filter. So you pour quite a bit of solution, run it through the ETN until there's no reaction at all. If you have a lot of reaction, you may want to consider dumping out the ETN into its own separate bath of sodium bicarbonate solution, 5%, and then mix it up, hand mix it to make sure that you get neutralization of any surface acids. And then in that case, if you did that, then you would just refilter. At that point, now that you have done a water wash to remove surface acid from ETN, and then you have checked it with a sodium bicarbonate solution, and there's no reactivity, your ETN is now stable enough to use immediately. So if you're going to fire this right away, you can dry it out and use it immediately. If you're going to, for whatever reason, store ETN at all, it requires additional processing. The additional processes for ETN include a recrystallization and a stabilization with a acid scavenger. These are both done in back-to-back operations. They sort of complement one another. So the way that generally I do this, I'll give you the generalities and then I'll tell you the specific dangers and techniques and procedures that I use. So generally, you will pick a solvent. You can, it's a wide world of sports when it comes to ETN solvents. You can use acetone, you can use any of the alcohols, so methanol, ethanol, isopropanol. You can use all this stuff. It's going to dissolve it really well. Acetone is a little bit aggressive in the way that it dissolves ETN. It kind of gives it a strange character, and I don't really like it. So I don't prefer to use acetone. Personally, I prefer to use isopropanol. It's a 90% concentration. It's pretty cheap. It's inexpensive. It's accessible where I'm located at. And isopropanol in my testing dissolves more ETN at the temperatures that you're going to be dissolving it at than ethanol or methanol. In terms of amateur energetics, they're definitely using ethanol as the preferred solvent to recrystallize ETN. That's by far the most common. As you're probably aware, in order to dissolve ETN in a solvent, you have to elevate the temperature of the solvent, because the higher the temperature is, the more ETN is going to dissolve into the solvent. This brings us all the way back to the issue of the melting point of ETN. So this is a very important part. It's kind of weighty on me in terms of my conscience. I want to make sure that you understand the danger of dissolved ETN in a solvent. So when it's dissolved in a solvent, you have a liquid explosive. ETN dissolved in solvent can absolutely detonate if you give it the right stimulus. If you spill it on an open heat source, something like that, you can cause a detonation, and if that happens, it's going to detonate the entire thing. And this has happened before. There are famous incidents that are recorded online, where this has occurred in the past. So when you're using ETN and heat in the same operation, you need to use a lot of care and be paying attention to what you're doing. My technique is that I keep the operation separate. So the heat operation is off to the side. I push it off to the side, and then I have recrystallization going on another side. The reason for the separation is to prevent ETN, either as a powder during handling or in its solvent form, from being introduced or coming into direct contact with the heat source. Now, the intermediary between those two, the heat source and the ETN, is going to be a water bath. A water bath, you have some different choices of vessels. Pyrex is very common, but I don't like using Pyrex because it can break. Even high quality Pyrex or lab glass, it can break, and the way that it breaks is from contraction and expansion. So when you heat a water bath in glass and then you remove it from the hot surface, and if you put it on a cold surface, if it's cold enough, it will contract, break the glass. You're going to get spillage of your hot water bath. And I want maximum physical stability when I'm processing ETN. I don't want anything breaking. I don't want stuff spilling out. I don't want any of that business at all. So I use stainless steel bowls. I picked these up from the hardware store. They're stainless steel dog bowls. They're really cheap. This is a small one, but you can get larger ones. They work great for a water bath. You can pour water in them, put it directly on the heat source, and bring it to a boil. Boil is a great temperature to bring your water bath to, because you can detect it with your eyes. You see when it's boiling, and then okay, kill the heat source, remove my water bath, and then I have a container with my solvent of choice, and I put that solvent into the hot water bath that was boiling. The temperature is going to rise. I'm going to use a thermometer in the solvent, and I don't want it to exceed, for me, I go 55°C. So there's, a 6-degree buffer before the melting point of ETN, and that gives me a margin of safety. So I bring the solvent to 55°C, I remove it from the hot water bath. It is going to slowly begin cooling immediately when it's removed from the heat source, the water bath. And I'm going to immediately start adding ETN by the spoonful with stirring, 1 spoonful at a time. Allow it to dissolve. It should dissolve completely and be see-through. And I don't have solubility figures for you on ETN. If you know of solubility figures for ETN, if you can post it along with the source in the comments, that would be really helpful. If you're adding ETN to the solvent and it cools off enough and you start getting ETN coming out of solution, you can reintroduce it to the hot water bath, but not on the heat source. You want to keep the heat source separate. So if your water bath cooled off and it wasn't hot enough yet, you can take the solvent and ETN out, obviously, put the water bath alone on the heat source, crank up the heat, boil it again, then remove it from the heat source and repeat the whole process. You want to keep that temperature below the 61°C of the melting point of ETN so that you don't have sensitivity issues. This is one of those factors that can be relieved by using acetones, where acetone shines, because acetone's boiling point is below the melting point of ETN. I just don't prefer it because of the morphology and issues with dissolving ETN that will become apparent if you go with an acetone method. Now that the ETN is dissolved in solvent, we have to crash it out to recrystallize it and turn it into solid morphology ETN. The way that we do this, because right now, as it's dissolved, any acid that was trapped inside of the crystals is now free in the solvent. So in the crash bath, we introduce an acid scavenger. The acid scavenger that's most commonly used and makes the most sense is urea. Commonly, people will use a 5% by weight urea solution with water. I think you can go up to 10%, and it's not going to make much difference. You'll just get a more effective scavenging of acid if you go up to 10%. So you prepare a water crashing bath with 10% by weight of urea. It's going to completely dissolve in the water. Once it's totally dissolved, you may want to add some ice to keep it cool, because the cooler it is, the more ETN is going to precipitate. And then you just pour off your ETN solvent into this crash bath, and it's going to precipitate ETN. And if everything went well, you should now have any acid that was trapped inside of the ETN crystals scavenged by the urea, and you no longer have contaminated ETN that's going to go through decomposition. People will go to extreme lengths to recrystallize and purify ETN, and it really is warranted depending on how stable you want it to be. If you don't remove all the traces of acid, you will get decomposition. If you had a huge pile of ETN that still had acid trapped inside of it, it can go into a fire and even detonation. Small amounts, you're just going to see yellowing on the edges of ETN. And the way to deal with the slightly decomposed ETN is just to recrystallize it again and crash it out into an acid scavenger bath. I don't have to deal with storage of ETN, so this isn't really a concern for me. But if I was in, some situation like a war-torn country where I wanted to make stabilized ETN for long-term storage, I would definitely, at minimum, do 2 recrystallizations with acid scavenger baths at the end. If you do it one time, you may have mixed results. You may have partial decomposition of your product. It just kind of depends on the particularities of the method that you set up to use for yourself and the reaction conditions that you do the reaction in. If done correctly, nitrate esters in general, including ETN, are shelf stable for years and years. I have made equivalent batches of PETN and ETN at the same time using approximately same methods. And after recrystallization, single process time, I have found that the PETN is completely stable, doesn't undergo any changes during testing, whereas ETN tends to go into decomposition if you don't give it that second recrystallization. So that essentially sums up my findings in production of ETN, things that you're going to experience or run into and what to expect. Now we'll go into application of ETN and usage cases.
ETN application.
ETN has a very unique property, several of them. One, it's melt castable, which gives it a high density. The melt cast density of ETN is 1.69 grams per cubic centimeter, somewhere thereabouts. At this density, you're going to get a detonation rate of 8 kms, which is very good for a nitrate ester. It's good for any explosive. 8 kms is excellent. So in cases where you would want the performance maximized for ETN, you're going to want to do a melt cast operation. Wait, Dugan, you said don't go to 61C. Well, what I'm talking about when I say that is I'm talking about, process handling of ETN. When you're purposefully melt casting it, you do it safely, and then you're not going to have any problems. Now, people will melt cast ETN and stir it and handle it and process it without incident, but because of its heightened sensitivity, I like to use standoff procedures as an extra margin of safety. Okay, in general, when I'm doing a melt cast explosive, the way that I've kind of developed to do this through trial and error is to use an electronic hot pan, analog, or digital controlled heated hot pan that doesn't get too high in temperature. So I've got an old analog one with a knob. It goes from very low temperature to about 120 C at the maximum. This is important so you don't accidentally decompose whatever you're going to melt cast and cause a detonation. The one that I'm using fits a Pyrex baking pan inside, which is fantastic because it's easy to clean. It's easy to remove the material from when it's done melt casting. I like to enclose the pan with a piece of glass on top. I typically use sets of refrigerator glass that I take off of trashed refrigerators that people throw away. I removed the glass from those, and they're very strong glass. They work really well for the purpose of enclosing the pan and creating a homogeneous heated environment that, you know, isn't just heated from the bottom while the top stays cool and causes issues with the milk cast. When you enclose it, the entire environment becomes the same temperature, and it becomes very easy to, you know, thoroughly melt materials together or milk cast a milk cast carrier for an explosive. So that's my preferred method. Because ETN is sensitive in the melt phase, I like to use standoff during the operation when I'm melt casting it. So for basic ETN use, I want to get it to that melt casted maximum density of 1.69. I'm going to put it in my hot pan, I'm going to cover it up, and then I'm going to turn on heat. And this hot pan is plugged into a circuit that then has a circuit breaker that's, you know, several yards away, enough to where if this thing detonated, you know, I'm not going to get hit by anything. So I kill power to the circuit. When it's done melt casting, it's going to come out of the melt phase back into the solid phase. ETN, if you're not aware, it's very sensitized to melt phase, but when it returns to the solid phase after cooling, it reverts back to nearly its original mechanical sensitivity. It is slightly more friction sensitive at that point, but for practical use, it's very similar to its original state. Much safer than ETN in the melt phase. The other property of ETN that should be exploited when you're making charges out of ETN is that ETN is an oxidizer explosive. We went into this with the advanced explosive design instructional video to give you an example of how to calculate balanced mixtures with an oxidizer and a fuel. ETN works best with a variety of fuels, so I'm going to list off some explosive fuels and some metal fuels that would be common, things that amateur enthusiasts would probably have access to or want to use in a composition. So I'm just going to list these out, and we're just going to put them all in one spot in this video for reference so you can reference it later. Hopefully none of these are in error. I did all these calculations myself, you know, kind of offhand, so hopefully there's no errors. I double checked them, but who knows. If you find an error, just list it in the comments, and then I'll put a correction in the video. The first one we'll talk about is ETN and PETN. PETN is very popular, so the ratio, and all these ratios are going to be first listing the ETN percentage and then second listing the fuel percentage. So ETN PETN, 65.65% and 34.35% for the PETN. Then on to ETN RDX. This is very interesting because the detonation products of RDX, 44% of them go to carbon dioxide and 56% of them go to carbon monoxide. So technically, the more correct way would be to calculate to carbon monoxide, but you're missing the 44% that goes to carbon dioxide. So I did some special math here to come up with the correct percentage ratio for ETN and RDX, and interestingly enough, it is 64.23% of ETN and 35.77% of RDX. So that's very similar to the ETN and PETN ratio. I guess I'll put all these ratios over here. Following up PETN and RDX, we have nitroguanidine, very common explosive that's very simple to make, much like ETN, so that probably has some practical application there. The ratio for that will be 85.24% ETN, 14.76% nitroguanidine. Aminonitroguanidine, much less common than nitroguanidine, but still it may be out there. 86.38% ETN, 13.62% aminonitroguanidine. Then we have TNT, 93.31% ETN, 6.69% TNT. And then we have ETN and aluminum, 94.38% ETN, 5.62 aluminum. ETN titanium dihydride, very exotic but available from pyrotechnic suppliers, a very cool material. 94.78% ETN, 5.22% of titanium dihydride. Nitrocellulose, this is for straight nitrocellulose, so this isn't a gunpowder that has nitroglycerin and nitroguanidine in it. 94.34% ETN, 5.65% NC. Charcoal, probably the easiest access fuel source. So ETN 97.83 and charcoal 2.16. And finally, ETN propylene glycol. Some of these mixtures I have no idea what they're going to do, so we'll just show it on the video, kind of the properties of, you know, physically what it's like. But this is 96.95% ETN and 3.05% propylene glycol. Glycols, there are several of them. There's ethylene glycol, diethylene and triethylene glycol in brake fluids and antifreezes. The propylene glycol is really interesting because you can order it over the counter and it's pure, and it's also non-toxic. So it's used in food processing, so it's very available. So that's propylene glycol. For all these mixtures that I'm showing, the general procedure is to mix the ingredients dry in a container and then put them in the heat source for milk casting, and then cooling the milk cast, allowing it to form a high density solid, which can then be flaked. So flaking involves taking a solidified material, it's going to reduce in its volume pretty considerably, and then you just break it up into grains. And when you pack this, if you make milk casted ETN and cool it, and then you're packing it into a detonator or an explosive composition, flaking it and packing it, even though you're breaking it up into granules, when you pack it in, it's still going to retain that high density. So you're going to get that maximum detonation velocity. In general, for milk casts, whatever, for ETN, any fuel that you add, if it's an explosive fuel, it's going to be at the density of the ETN, so 1.69. That's where that material is going to be in terms of its performance, but the interaction between the oxidizer and the fuel, both of them being explosive, is kind of unforeseen and it needs testing. We're going to test some of these mixtures, but I'm going to do it in a later video because this video is just entirely too long. So I hope you enjoyed this. This was ETN part 2. I'm glad to get this out of the way. Moving on.